everyone, welcome back to Math 251. Today is a big day because we have moved on to chapter 4 of the textbook. We are done with chapters 2 and 3. This is chapter 4, section 4.1. Our mathematician of the day is Mary G. Ross. She was the first Native American female engineer and received her degree in math at Northeastern University, which was founded by her great-great-grandfather who led the Cherokee tribes during their forced removal. What an awesome person. And did you know that the first instances of the Pythagorean theorem can be seen in Babylonian clay tablets from 2000 BC? What? Wow, they really knew their stuff, didn't they? So we're shifting gears a little bit. We are still obviously going to be talking about derivatives, but chapter 4 is mostly about graphs. So we are going to be focusing on graphs. Today we'll be talking about maxima and minima. So we have a definition to start us off. Let f be defined on a set or an interval D containing a point C. If for every x in D we have that f, oops, my pen is not working, there we go, f of C, I cannot write apparently, f of C is greater than or equal to f of x, then we say that f of C is an absolute maximum of f on this interval. If for every x in D we have f of C is less than or equal to f of x, then f of C is an absolute minimum of f on D. An absolute extrema value is either an absolute minimum or an absolute maximum value. So let's draw some pictures here to see what it means to have an absolute maxima or an absolute minima. So say I have a graph like so, something like this. So this is kind of like an upside down quadratic function. This point right here is my absolute max because on my interval, which according to my arrows is from negative infinity to positive infinity, this f of C value is greater than or equal to all of the other y values on this graph. So this is our absolute maximum value. However, since our graph goes on forever in the negative direction, we do not have an absolute minimum value because we continue to get smaller and smaller and smaller. So no absolute minimum. All right, let's look at a graph like this. So say I have a closed circle there and a closed circle there. Well, obviously this right here would be our absolute max, since it is the highest y value on our whole graph. Here we have a closed interval, right? We're not from negative infinity to positive infinity. And this is my absolute min. So it's important to note here that my interval is closed. I have a closed circle here, and I have a closed circle here. That's important to note because if I were to have a graph like this with an open circle here and an open circle here, then I do not have an absolute max or an absolute min. Because as I get closer and closer and closer to either of these closed circles, I approach what would be my maximum or minimum value, but I never actually reach it. So if I have open circles, this is an open interval, I do not have an absolute max and I do not have an absolute min. This is important. No absolute min and no absolute max. And finally, if I have a graph that looks like this, then I have an absolute min here. That's the smallest y value. But because my y values continue to get bigger according to those arrows, I do not have an absolute max. So when we're dealing with absolute maxima and minima, this is the maximum or minimum point on the entire graph. So we are going to be talking about something else here in a minute that's a local maxima and minima, but absolute maxima and minima is the highest or lowest point on the entire graph for its domain. All right, next we have a theorem called the extreme value theorem. A function that is continuous on a closed interval, very important that it's closed, that means that I have closed circles on either one of my endpoints. So a function that is continuous on a closed interval from a to b has an absolute maximum value and an absolute minimum value on that function. Excuse me, on that interval. So kind of like this graph right here, this graph is continuous and it's a closed interval, right? We have closed circles on either one of those endpoints. So we did have both an absolute maximum and an absolute minimum value on this interval. All right, let's look at an example here. For which x value does the following function have an absolute minimum or an absolute maximum value? So I'm going to add some endpoints here to make this a closed interval. So this graph is a continuous function, and we are on a closed interval between -4 and 5. So I know that according to the theorem right above, that I do have an absolute max and an absolute minimum value. So my absolute max, the highest point on the graph, occurs at x equals 4. And my absolute minimum occurs right here. That is at x equals 2. And again, this would not be the case if I had arrows in this direction and in this direction, because then it would not be a closed interval. It's very important for this theorem that we are dealing with a closed interval. That's why we needed those closed endpoints on this graph. All right, next we're going to look at the definition of a local minimum or maximum. So here we are on some interval. So suppose C is an interior point, or just inside some interval I on which our function is defined. If for all x in I we have f of c, f of c is greater than or equal to f of x, then we call f of c a local maximum of f. If for all x in I we have f of c is less than or equal to f of x, then I call f of c a local minimum value of f. So the difference between an absolute minima and maxima and a local minima and maxima is that an absolute extrema is the highest or lowest point on the entire graph. A local maxima or minima is the lowest or highest point on a region of the graph. So we can have multiple local maxima or minima values on the graph. In fact, usually we do. So let's use this graph to find which x values this function has local and absolute minima and maxima values. So let's pretend that these arrows go on forever. This is the graph of x to the power 5 plus 3.5x to the power 4 minus 2.5x cubed minus 125x squared plus 1.5x plus 9. All right, so we want to find the local max, local min, and absolute max and absolute min. Well, first of all, since I have an arrow down and an arrow up, that's telling me that I am not on a closed interval, so I'm not guaranteed an absolute max or an absolute min. And because I have one in the positive infinity and one in the negative infinity direction, I don't have either one, right? My x values are increasing on this side forever and decreasing on this side forever. So I don't have an absolute max or min. I do, however, have some local maxes and mins. So a local max or min is the highest or lowest point on a certain region of the graph. So I have an absolute max here. That's the highest point on a certain region, and here. So I have local max. It's okay to have multiple of them, so that looks like it's x equals negative 2.5 and x equals 0. And then our absolute minimum values are here and here. Sorry, did I just say absolute minimum values? I meant local minimum values. Local min at x equals negative 1.5 and x equals 1.25. About. So these local mins occur at the lowest point of a certain region of the graph. And you might be noticing that these local maxes and mins occur wherever I have a horizontal tangent line, right? So that is our next theorem, the local extreme value theorem. If f has a local max or minimum value at c, and f prime of c exists, then f prime of c is equal to 0. So if I have a local max or min at a certain point, then I am guaranteed that the derivative of that point is equal to 0. All right, next we're going to define what it means for a function to have a critical point. So an interior point C of the domain f at which f prime of c is equal to 0 or f prime of c does not exist is called a critical point of f. So we will be talking about critical points in the next several lessons, actually, but we will talk about it here shortly. I want to go back, however, to this local extreme value theorem for just a second. So it says, if f has a local max or min value at c and f prime of c exists, then f prime of c is equal to 0. This is true. It's always true. However, the converse, or the opposite of the above theorem, is not true. What does that mean? Well, just because f prime of c is equal to 0 does not mean that I have a local max or min there. So just because I have f prime of c is equal to 0 does not mean I have a local min or max. So for example, if I have a function that looks like this, at this point right here, c, we'll say, here I have f prime of c is equal to 0, but that point is not a local max or a local min. So f prime of c is equal to 0, but not a local extrema. We'll learn what this is called. This has a special name. It's point C. Okay, and also, what about if I have a derivative that does not exist? So if I have, I'm really bad at drawing these, but say I have a vertical tangent line. So something like this vertical tangent line. So here, the derivative at the point C does not exist since I have a vertical tangent line, but I don't have a local max or a local min at this point C. So here f prime of c does not exist, but no local max or min. So it's important to remember that this theorem here only goes one direction. If I have a local max or min and our derivative exists, then our derivative is equal to 0. The opposite is not true. All right, so remembering that a critical point is where f prime of c is equal to 0 or where f prime of c does not exist, let's find the critical points of f of x is equal to x cubed times natural log of x. So I need to find the derivative and see where it fails to exist or where it's equal to 0. So I see that I need to take the derivative using the product rule. So I'm going to set f equal to x cubed and g equal to natural log of x. That means f prime equals 3x squared and g prime equals 1 over x. So I get that f prime times g plus g prime times f is equal to 3x squared times natural log of x plus 1 over x times x cubed. We can rewrite this, simplifying these second two terms. This is 3x squared times natural log of x plus x squared. And then from this, I can factor out an x squared. Since I want to set this equal to 0, I do want to simplify it as much as possible and factor it as much as I can. That will make solving for 0 easier. So when I factor out an x squared, I'm left with 3 natural log of x plus 1. So is there anywhere that this does not exist, this derivative does not exist? No, there's nowhere that this derivative does not exist. So I don't have to worry about that part. All I need to worry about for my critical points here is finding where our derivative is equal to 0. So I'm going to set this expression here equal to 0. So I get x squared times 3 natural log of x plus 1 equals 0. This means that, let's see, if I set each factor equal to 0, I get x squared equals 0. Which means that x is equal to 0. That is one critical point. And if I set the other thing, 3 natural log of x plus 1 equal to 0, that's our other factor. Well, I'm going to subtract 1 to get 3 natural log of x is equal to negative 1. Divide by 3 to get natural log of x is equal to negative 1/3. And to solve for x here, I raise e to the power of both sides, so I get e to the negative 1/3 is equal to x. So our critical points here are x equals 0 and x equals e to the power of negative 1/3. So at these critical points, some important stuff happens that we will talk about in the coming lessons. But for now, we are just calling these our critical points. So how do we locate absolute extrema on a closed interval? So here is our procedure. How do we do this? So I first need to make sure that f is continuous on our closed interval. So assume f is continuous on this interval. And then I can do this procedure. So first, I locate the critical points using like the method that we just used in example 3. Locate the critical points C, we'll call them C, in our interval from A to B, where, remember, by the definition of a critical point, so this is where f prime of C equals 0, or f prime of C does not exist. That's step 1. Then I evaluate f at these critical points. And at the endpoints A and B. A and B. And then finally, I choose the largest and the smallest values of f from step 2 for the absolute maxima and minima. Values of f from step 2 for absolute max and min. So this is how I find the absolute extrema on our closed interval. I locate the critical points by seeing where our derivative is equal to 0 or does not exist. I evaluate f at these critical points and at the endpoints A and B. And then I compare all of those f values to see where I have the largest one and where I have the smallest one. Alright, so let's do some examples here. So we want to find the absolute and maximum and minimum values on f of x is equal to x to the power of 4 minus 3x cubed on the interval from negative 2 to 2. So following my procedure here, I first need to find the derivative and set it equal to 0 and find where it's undefined, if it is. So I see here that f prime of x excuse me, is equal to 4x cubed minus 9x squared, using the power rule there. And first of all, I see that since this derivative is a polynomial, it is defined everywhere. So I don't have to worry about finding where f prime is undefined. So I set this equal to 0. This is easiest if I factor. So what can I factor out of both of these terms? I can factor out an x squared. That will leave me with 4x minus 9 equals 0. Setting each of these factors equal to 0 gives me x equals 0, and x is equal to 9 over 4. So these are my critical points. That was step 1 in this procedure. Step 2 is I need to evaluate f at these critical points and at our endpoints a and b. So let's do these two critical points first. So I see that f, our original function, evaluated at 0, is 0 to the power of 4 minus 3, 0 to the power of 3, which is equal to 0. I see that f of 9/4 is equal to 9/4 to the power of 4 minus 3 times 9/4 cubed, which is equal to, if you type this into your calculator, negative 8.55. Okay, so those are our two critical points. Whoops. And now I need to see what's going on at my endpoints, just in case. So f at my first endpoint, negative 2, is equal to negative 2 to the power of 4 minus 3 times negative 2 cubed. This is 16 plus 24, or 40. And f of our other endpoint of 2 is 2 to the power of 4 minus 3 times 2 cubed, which is negative 8. So I have to pick the largest of these f values. Obviously that's 40. So I have an absolute max at x equals negative 2. And I pick the smallest y value here. That's negative 8.55. And that means that I have the absolute min at the point x is equal to 9/4. Why do I have to check the endpoints here? Well, it's possible that my function is decreasing or increasing on near the endpoints. And so, for example, this is a polynomial, so I know that it will increase forever either in the positive or negative direction. So I have to check the endpoints to make sure that that I'm not reaching a max or min there. And in this case I was, right? I had the absolute max at x equals negative 2, probably because at x equals negative 2, my function was going off towards infinity. Alright, I'd like for you to try example number 5 on your own before we do it together, so pause this video and give it a try. Alright, hopefully you tried example number 5. So I have g of x is equal to x to the power of 2/3 times 4 minus x. I could use the product rule on here in order to differentiate it, but I am going to multiply it out first. So I see that g of x is equal to x to the power of 2/3 times 4 minus x. Again, you could use the product rule here, no problem, but I am going to multiply it out. So this is equal to 4x to the power of 2/3 minus x to the power of 5/3. And I want to find this derivative, so g prime of x using the power rule here is equal to 8/3 times x to the power of negative 1/3 minus 5/3 x to the power of 2/3. All right, now this is tricky, but here is how I want to simplify this a little bit to make it easier to solve for when f prime is undefined or equal to 0. So I see that both of my x's have a 1/3 in them. So what I'm going to do is I'm going to write this as I know that it has to be a rational function with something on the bottom since I have a negative in front of that x to the power negative 1/3. So I am going to put a x to the power of 1/3 in this denominator here. Also, I'm going to put a 3 down here since I have 8/3 and 5/3. So then how do I write 8/3 x to the power of negative 1/3 if I have 3x to the 1/3 in the bottom? Well, 8/3 x to the power of negative 1/3 is the same thing as if I just put an 8 here, since the 1/3 in the bottom here makes that a negative. So that term is taken care of, and then I will have 5 minus 5, that 5/3 is taken care of, and I will have an x to the power of 1 here, since if I have x divided by x to the power of 1/3, this is x to the power of 2/3, since I subtract my powers here. So this is another way to write this expression, 8 minus 5x divided by 3x to the power of 1/3. This is my derivative, and in order to find the critical points, I need to find where this derivative is undefined and equal to 0. Well, I see that it's undefined when my denominator is equal to 0. So when 3x to the power of 1/3 is equal to 0, g prime of x is undefined. And when does this happen? 3x to the power of 1/3 is equal to 0 when x is equal to 0. So this means x equals 0 is a critical point. In order to find where g prime of x is equal to 0, that means I set the numerator here equal to 0. So g prime of x equals 0 when 8 minus 5x is equal to 0. This means that x equals 5/8 is a critical point. So these are my two critical points, and I also have two endpoints here. So next I need to evaluate my function at these 4 points. So f of 0 is equal to 0 to the power of 2/3 times 4, which is just 0. F of, 5/8 is equal to 5/8 to the power of 2/3 times 4 minus 5/8, which is equal to 2.4671. Those are my two critical points, and then I have to evaluate at the endpoints as well. So f of negative 1 is equal to negative 1 to the power of 2/3 times 5, which is equal to 5. And f of 2 equals 2 to the power of 2/3 times 2, which is equal to 3.174. So my biggest value here is 5. My smallest one is 0. That means that I have a local max at x equals negative 1 and a local min at x equals 0. This one was a little bit tricky because of simplifying that rational function, but the process was the same. We found our derivative, we set it equal to 0, found our critical points, tested those critical points and the endpoints, and then we had our absolute I wrote local, didn't I? Minimum and maximum values. So this should be absolute. Absolute. They're also local, but oops. Absolute. All right, we have one more example. A spoon is launched vertically upward from a bridge 80 feet above the ground. Why? I don't know. At a speed of 64 feet per second. Its height above the ground t seconds after the launch is given by the equation f of t is equal to negative 16t squared plus 64t plus 80 for t between 0 and 5. When does the spoon reach its maximum height? So I need to find the derivative of this, set it equal to 0 to find my critical points, test the endpoints, and then see when I have this maximum height. So another way to think about this maximum height is the absolute max. So my function here, f of t, is equal to negative 16t squared plus 64t plus 80. That makes f prime of t equal to negative 32t plus 64. This is a polynomial, so it's always defined. So to find my critical points, I set this equal to 0, and that means that I have negative 32t equals negative 64, which means t equals 2 is my only critical point. So to find when it reaches the absolute maximum height, I need to test this critical point and the two endpoints. So f of 0, my first endpoint, since I'm only defined from 0 to 5, is equal to 80. F of 5 is equal to, if I plug in 5 here, I get 0. And if I plug in 2, I get 144. So obviously this is our local max. So my maximum occurs at time equals 2 seconds. All right, well, I hope you enjoyed today's lesson. I know that I did, all about local and absolute max and mins. If you have any questions, I would love to answer them at our Zoom meeting, so come on over there. Other than that, I will see you on Friday. Have a good day.